screen, and good evening again. We're going to look on latent heat and what latent heat is involved in. If you notice that latent heat has two things, let's look on this word, late. And we're going to look at latent heat as late heat. What does it mean? When you heat a substance under laboratory conditions, for example, we're heating ice, and if we're supposed to stick a thermometer in it, and we're looking at pure water, and we heat it, heat is being added to the system. And what we believe is that if we're looking at pure water, it will be at 0 degrees Celsius until all the ice has become into a liquid. So pretty much we're not going to see a change in temperature until the change of state has completely finished. Some people might say, oh, this is strange, but we actually observe this more readily when we look on water in its liquid form, and people do agree with this. So as I heat water, we're going to see the temperature going up, and we normally say at 100 degrees Celsius water boils, and we won't see the temperature of the water passing that 100 degrees Celsius until everything has gone into a steam. So we're used to it when we're looking at water boiling. But if I tell you the same thing for ice, well, we have to have some conditions here to actually get this. But what we observe is that when you reach a boiling point, a melting point, or a freezing point, or any of these points where there's a change in state, there is no change in temperature. And that is called late heat. Or physics term is actually latent heat. So it is let's look at it. It says when a substance changes state, heat is usually added or removed. The change of state or phase usually takes place at a constant temperature. Latent heat involves the amount of heat energy needed to change the temperature of, to change the state of a substance. And that's what late heat is about. Now, let's look here. Now, last time when we look on heat capacity, we'll look at heat capacity and we'll look on specific heat capacity. What I said is that heat capacity look at the amount of heat energy needed to change the temperature of a substance by 1 degrees or 1 Kelvin, and specific heat capacity is the amount of heat energy needed to change the temperature of 1 kilogram of a substance by 1 degrees or 1 Kelvin. So when you see specific latent heat or fusion, well, we're going to talk about latent heat, the fusion part. When we see specific, we're going to talk about 1 kilogram. And we'll see that we have the latent heat down here again, and we're talking about 1 kilogram. So once you see the word specific, we're talking about, in the definition, there'll be 1 kilogram there. Now, because there are changes in phases, for example, let's look solid, liquid, gases. Each of these have different names. For example, moving from here to here, we'll talk about the specific latent heat of vaporization. So moving from here, we'll talk about there will be vapors. So we'll talk about specific latent heat of vaporization. So that's where we get this name from, vaporization. Fusion, we normally look on how it is moving from liquid to solid. And later on, you might hear about condensation. You might talk about solid to liquid, or you might talk about I don't remember this one, but later on I might come across it. All right. So all these terms are just the changes that we're moving from one form to another, and they're normally terms that we'll get used to. So fusion is when the amount of heat energy needed to convert 1 kilogram of a substance at a fixed temperature. Give me a second. At a fixed temperature to change it from a solid to a liquid. And give me a second. So let's look on latent heat or vaporization. There's an equation for them. One is going to be called EH, or heat energy, is equal to mass times the latent heat of vaporization. Depends on the substance, it will change. This is for specific latent heat of vaporization. Or EH is equal to the mass times specific latent heat of fusion. And those are some of the equations. These will be constant, and the SI unit will be in joules per kilogram. Here's a lovely question. Calculate how much heat energy is needed to change 20 grams of ice from -20 to 100 degrees Celsius of steam. And this is going to be a quite more difficult question than you might think. Give me a second, let me change. This is going to be quite interesting question. Right off the bat, we're going to look on certain things. So we have ice. We're looking on ice. In terms to move from ice to steam, we're going to have a few things happening. So we're going to have ice. We're going to have a solid ice. Then we're going to have a change of state, and that's going to be called melting. Then after that, we're going to have liquid ice. We're going to have a water. Actually, let's call it water. And that's going to be a liquid. And then we're going to have a change of state. And we're going to have that called, let's call it vapor. We're going to have vapor being formed. We're just going to use the word vapor there. So we'd have to account for the changes here. So we're going to have we're going to have a change in state here. We're going to have a change in state here. We're going to call this vaporization. Let's vaporization. And then we're going to have fusion. We're going to have fusion right there. I spell that right. We're going to have some problems using that. Let me show you something. I'm going to draw what we'll call a cooling curve or a heating graph. Normally, let's call both of them cooling curves. In chemistry, we normally get technical, but it's going to be cooling. Let's call it heating then. I prefer, instead of writing in words, I prefer drawing a diagram for it. It's got a diagram I'll draw. So I'm going to come here. I'm going to stay right here. And it's going to be my 0 degrees Celsius. This is going to be my 100 degrees. And also, this is going to be my -20. I'm going to put the other things in red. So what's going to happen? I'm going to have a change in temperature that goes from here to here. Because I know that ice is going to melt right here. So I'm going to put time here. I didn't put time there. And it's going to be put temperature in degrees Celsius. So if I plot it there, I'm going to observe that ice will absorb some heat. And then afterwards, it's going to plateau. So this portion represents the change of state. Then after all of it changes, it's going to go up here. It's going to reach the 100, and then it's going to start to boil. And when it boils, it's going to plateau and changes into steam. So if I'm going to look in the container, I'm going to say ice. Let's imagine that. What we'll see right here, we're going to see two things. We're going to see ice and water. And if I look in the container right here, I'm going to see water. And if I look right here, all I'm going to see is steam. So it's a process. So we're going to heat it. We're going to say ice. Then the ice is going to melt. And then after it melts, all of it is going to turn water. The water is the temperature is going to raise. And then we're going to have steam. And we need to account for all of this. Now, latent heat only account for two portions of this graph here. This portion here and this portion here. Those two portions are latent heat. So we can use this equation. EH is equal to MLF, and Cx would need to give you this constant. And then right here, this heat portion would account for EH is equal to ML. Sorry, that's LF. My bad. And this is LV. I don't know. This is vapor. Vapor. V for vapor. I'm gonna pause this video. But we have a problem. Let me erase a few things so it doesn't look that confusing. We have a problem though. Although we accounted for the latent heat, we actually have heat is being absorbed here and heat is being absorbed there. But we haven't look on that with latent heat. No, we're gonna end up with a scenario where we need specific capacity. If you remember specific capacity equation that links specific capacity, you're gonna say heat energy is gonna be equal to mc delta T. So right here, so here we're gonna have a change in temperature, and the change in temperature would have been 100. And here, I can use mc delta T, and I'll have a change in temperature, and the change in temperature here would have been equal to 20. I have another problem you might not think about though. All this ice and water have different specific capacity. They're going to behave differently. So C would be different. So the C here, the value for C here, this would be the specific capacity of water, and this C here would have been the specific capacity of ice. So they're going to behave differently. Just like LF is the specific latent heat of fusion, and LV is going to be the latent heat of vaporization. So using these so it's going to be one equation, 1, 2, 3, 4. We need to account for 4 things in order to calculate the total energy needed to raise the temperature of 20 grams of ice from -20 to 100 degrees of steam. So we know, if we can imagine it, we're gonna have ice, it's gonna melt, and whenever you have a change in temperature scenario, we use this equation. That's why I put it here. Change in temperature. So this is change in temperature. That equation takes there. Bam. Next part happening, we are having a change in state. It's moving from a solid to a liquid. Therefore, we're gonna use latent heat of fusion. After that, we're gonna have the ice. All of the ice melts gonna have water. It's gonna raise the temperature again. We have a change of temperature. This is our change in temperature equation. And then last but not least, it also said that it became steam. So it's not water anymore, it's steam. And therefore we're gonna use latent heat or vaporization. So it had to absorb some heat to change the state. So we're gonna end up calculating all this. In order to calculate this, we're gonna need some constant. We're gonna need I'm gonna write them down soon. We're gonna need the specific capacity of ice. We're gonna need the latent heat of fusion of ice. We're gonna need the specific capacity of water. We should know that already. And we're gonna need the specific latent heat of vaporization of steam. So afterwards, we're gonna write that down. So I'll meet you guys in video 2, where we'll actually answer these questions. Ensure to like and subscribe. Leave a comment in the comment section. See you next time.